Hi, this is SJ Bennett, aka Quellism, and today we'll be using sound to drive animation in Blender. In this tutorial, I'll go over the bake sound to F-curves function and some of its options, demonstrate ways of using the resulting data within objects and armatures, and give you a whirlwind tour of the audio spectrum. At the end, we'll be using the baked F-curves to drive character animation of a drummer using data sourced from a single sound file containing a drum track. But first off, let's use bake sound to F-curves with its default options. We'll make the default cube bounce mindlessly to dance music. So, select the default cube in object mode, then go to the transform panel located in the N menu. Find the location parameters, right-click Z to bring up a menu, and then select Insert Single Keyframe. This creates an animation channel on Z location that we can bake F-curves to. Go to the Graph Editor, click on the Key menu, and then click on Bake Sound to F-curves. I have some music here that I've prepared earlier. It's house music, so it has a strong 4-on-the-floor beat, which should show up very obviously. There's also options like attack and release, but we'll get to those later. For now, just click Bake Sound to F-curves. So what Blender's done here is analyze the music and seen how loud it is at any given frame and turn that loudness into animation data. So let's go back to the 3D view and press Alt-A to make the animation play. So now the cube is moving and that movement is driven by the sound file. Although I'm not really liking this silent disco effect very much myself. So let's go back to the Graph Editor. Press E while hovering over the timeline to set the end frame to wherever the cursor currently is. So let's make it so we can hear the music. It's actually pretty good, I think. Go to the Video Sequence Editor, click on the Add menu, then click Sound. We'll use the same sound file we baked F-curves from and then add the sound strip. This happens sometimes. The cursor's not at frame 1, so it's inserted the strip wherever the cursor is. You just go back to frame 1 and press Shift S to align the currently selected strip to wherever the cursor is. Okay, now that we've fixed that, we can go back to 3D view and then press play or use the Alt-A hotkey to watch the animation with synchronized sound. Okay, enough hijinks. That's what bake sound to F-curves does. It figures out how loud a sound file is at any given moment for a given frequency range, smooths the bumps out using attack and release, then puts the result on an animation channel, which could be an object's position, a color's hue, emission strength, even a filter's blur size in the compositor. But how do we use this for character animation? Well, let's ask Mr. Googly Eyes. Well, there it is. Okay, I can't understand what he's saying, but I can tell you how he's saying it. This is Mr. Googly Eyes' armature. There's a head bone to keep his head still, and there's a jawbone rotating on its x-axis. You may have noticed that the x-axis is purple. That's because we're using a driver. The driver's copying data from here, a utility bone off to one side with a property called sound. This is where I've baked the F-curve containing his dialogue. We're using a driver so we can alter the raw data before it's used for animation. Now there's a lot of ways to alter that data, F-curve modifiers and constraints to name 2, but I'm using a scripted expression in the driver itself. Because it allows Python in its input, it lets me do quick and powerful experimentation to get the result I want. Using a driver also lets us reuse the animation data anywhere, for instance to make his eyes light up as he speaks. Assuming you've never used drivers before, let's have a gentle introduction on how to get animation data from one place to another while adapting it along the way. They're a very useful feature and definitely worth knowing. We'll start from just the bare rig, then we'll bake the sound and set up the driver to move his jaw. In pose mode, make sure you're not in edit mode, look for the blue. Select the utility bone and go to custom properties over in the properties panel. Click add, and then we'll edit the property. We'll fill in some of the properties. Sound is a good name. Its value can be 0, max can be 2. And you should always put something useful and relevant into the tooltip so you instantly know what this property is for if you come back to it months later or not. Now we hover over the property and press I to insert a keyframe. This turns the property yellow, which means it's ready for animation data. We switch to the graph editor, then we go to the key menu, then select Bake Sound to F-curves. We hit Bake, and now we have our data. We can see that this sound doesn't go all the way down to 0 when it's quiet. It has a visibly high noise floor. We'll filter away the effect of the background noise as part of the driver. Speaking of which, we'll need to right-click on the sound property and select Copy Data Path. We'll be using the data path shortly and you'll actually get to see what it looks like. Back in 3D view, right-click on the jawbone and clear the rotation back to 0. Right-click on the parameter again and select Add Single Driver. Back in the graph editor, we switch from F-curves to drivers mode. We click on X Euler rotation to select it, and now we see a drivers panel. There's a driver output at the top, input variables in the middle, and modifiers at the bottom. This is an input for the driver. We can use lots of them if we want to, but we'll only be using one for this. We'll change from transform channel to single property. Then we'll tell the property we want is in armature. Then we paste in the data path of the sound property of our utility bone. We can now see 0.019 as the property's value for this particular frame, and if we scrub between frames, it changes. As the voice rises and falls in volume, we can see the value of the driver input rise and fall with it. But the driver value doesn't change, it's still 0. A quick tip here, for troubleshooting this, make sure Show Debug Info is ticked. So what's up with the driver value sitting at 0 then? Well, the driver type is currently set to scripted expression and expr is set to 0. Whatever's in expr is our driver value. If we change expr to over 9,000, for instance, the driver value becomes over 9,000. But we want it to use our variable, so we put the variable's name, var, in expr. From now on, the driver value should copy var's value from frame to frame. So now the driver value is var. Excellent. Let's just visually confirm that the driver's doing its job and moving Mr. Googly Eyes' jaw. Great. But unfortunately, his jaw is trembling when he's not saying anything. This screen capture's not that great, but trust me, it's moving and we don't want it to. If he's not talking, we want his jaw to be closed and unwobbly. We have to tell Blender to ignore any values from var that are smaller than the noise floor. As I hinted at before, there's a few ways to do it. We'll use a scripted expression with the max function. Here we go. Max, round bracket, 0, var, minus 0.5, sorry, 0.05 actually, close round bracket. Enter. That'll do it. Let's take a look at what the value of var and the driver value are doing now. The value of var is currently 0.478. The driver value is 0.428. That's a difference of 0.05, just like in the expression. On this frame, it doesn't have that much of an effect. So you might wonder, what's the point of subtracting 0.05 at all? Well, but by using max in the expression and subtracting 0.05 from var, the driver knows to treat any frames with values of var less than 0.05 as 0. This has the effect of hiding the subtle jitter. In audio processing, we call this a noise gate. Now, there is a threshold option in the Bake Sound to F-Curves import options, which does more or less the same thing as this, but that would involve much more trial and error to get right. So let's take another look at the 3D view and make sure Mr. Googly Eyes' jaw is completely still when he's not talking. That's completely still now, which is exactly how it should be. We can now claim supreme victory over unwanted noise in our F-curves. We can make the jaw do other things while we're playing with scripted expressions. While we're experimenting, we'll want the graph editor and 3D view both visible at once, so we can see what the effect of changing the scripted expression is in real time. Blender's window handlers make this very easy. If we want the jaw to open up more, we can multiply the expression by 2. If we want the jaw to stay more open, even at rest, we can add to the expression. If we want the closed jaw to rotate past what is sensible, we can subtract from the expression instead. Scripted expressions are powerful little beasts, so don't be afraid of some basic maths and Python functions. So far we've covered object-level animation and armature-level animation using baked sound, both with and without drivers. But before we can become true power users of Bake Sound to F-Curves, we need to know a little bit more about the audio spectrum itself. When we talk about the audio spectrum of any given sound, we're ultimately talking about two characteristics, frequencies and amplitudes. The amplitude of an entire sound describes its overall volume. Most sounds we hear vary their amplitude over a whole frequency spectrum, and much like light, certain amplitudes and frequencies are far more sensitive for human ears than others. Let's have a listen to and a look at the frequency spectrum in isolated chunks. Energy at lower frequencies from, let's say, 20 to 300 Hz contributes bass or bottom end. Mid-range frequencies from 300 to around 5000 Hz contribute mid. There's no other good name for it, just listen. Higher frequencies from 5000 up to 20,000 Hz, the limit of average healthy human hearing, contribute treble or top. Certain frequencies dominating over others gives a sound its general timbral characteristic. For instance, a bass drum is almost all bass, and just a little bit of mid or treble at the attack or beginning of the sound. A hi-hat, on the other hand, is almost no bass, a bit of mid, and a lot of treble. Sounds with a pitch, for instance notes on a piano, have dominating frequencies which line up, they're harmonic. Sounds without a definite pitch, for instance the sound of a waterfall, have a diffuse spread of frequency activity instead, they're inharmonic, also known as noise. Many sounds actually have both harmonic and inharmonic components. Human speech, for instance, has both a harmonic component that comes from the voice box, think sounds like ah, and e, and an inharmonic sibilant component, sounds like s, f, and k. Some speech sounds make use of both at the same time, z, zh, v. Knowing the frequency peaks and patterns of specific sounds, in vowels they're called formants, is how phoneme detection works. If you want to know more about this sort of stuff, Google vowel formant frequencies and grab some popcorn. It's going to be an exciting night in for you, sir, or madam. The kick drum, snare, and hi-hat of a drum kit correspond fairly well to a bass, mid-range, and treble frequency, if not perfectly. So, given an isolated drum track, can we animate someone at a drum kit using a drum track for the source audio, baked as F-curves, and sent to the rig via drivers? Well, we could certainly give it a shot. To work out which frequency sounds loudest for which instrument, you'll need to analyze the audio. I'm using Audacity with the LADSPA plugins for Windows installed. We're going to be using a LADSPA plugin called the Glame Bandpass Filter, though any bandpass filter will do hypothetically. To be honest, this solution is not as quick and friendly as my preferred option of an actual digital audio workstation using a filter plugin with a GUI, but I can at least demonstrate this using an open source and cross-platform software pipeline with a workflow that anyone can replicate for themselves. So let's load the file into Audacity. Aha, it's already loaded. We'll start by looking for the woodblock. I think I heard it right there. Yep. Now, the woodblock is a harmonic sound with pretty much all of its energy concentrated in one single part of the spectrum. We know this because the timbre of the woodblock is more or less a beep, the same as a whistle or the sound the television makes when someone says "f***." These sounds sound the way they do because their frequency energy is very focused. This should make it easy to find in a spectrograph. Let's hit Analyze, then Plot Spectrum. And there we have it. If we look at log frequency, turn up the size to make the analysis more precise, but not too precise apparently. Then we get this very clear peak at around 2494 Hertz. Write that down in your copybook now. So, 2494 Hertz we can test out by attempting to bandpass filter it. If we're right, Control A to select everything, then 2494 Hertz will be a point where the woodblock is much, much louder than everything else. So let's look at the bandpass filter. First, we put in 2494 before I completely forget that number. So we have a center frequency here, we have bandwidth, and we have stages. We're not going to worry about stages because Blender doesn't worry about stages either. The center frequency of 2494 is the central frequency that the bandpass filter operates on, and the bandwidth is how many hertz either side the bandpass filter will actually work on. If we hit preview, we can hear fairly clearly that the woodblock is the loudest thing at 2494 Hertz. Just cancel out of there. So now we know 2494 Hertz is where we can find the woodblock at home. Let's do the same thing again for the kick drum. It's no real good to just analyze it because the kick drum is on more or less every beat, but we can probably isolate it with the bandpass filter. It's a bass sound, so we know the frequency is going to be on the low side. Let's start at 150 Hertz, and let's keep the bandwidth at 20. From listening to that, it sounds as though the kick and the snare are roughly the same energy. That's a lot of crosstalk that we don't want. Let's go down a little bit further to 80 Hertz. The bass is a lot more prominent, but we can probably isolate it further by, as Leonardo DiCaprio once said, going deeper. Let's go right down to 50. .50 Hertz sounds good. Now for the snare drum. The snare drum is a noisy sound with a very diffuse set of frequencies in action. Let's try a mid-range at around 1000 Hertz. There's a lot of crosstalk there from other instruments, so it's no good. How about 500 Hertz? Still not sure about that one. We can check the relative amplitude by applying the effect, then going to normalize to make the sound as loud as we can without altering its overall relative amplitudes. So, apply the filter there, and go up to normalize. Click OK. There's blur size in the compositor, but how do we use... Okay. I'm not sure about that because you can see the peaks of the bass drum here and you can see the peak of the snare drum there, and there's really not much in it. Let's reverse that and have a look at 275 Hertz instead. Okay, so I worked out some of this before I started recording. So what? Okay, that sounds like a much more certain thing. Let's apply that. Go back up, hit normalize, hit OK. Look at that. We appear to have found the punch frequency of the snare. Punch frequencies are very useful because they contain a lot of energy at the very initial part of the sound, which we call the attack. We'll be getting into attack and release momentarily. So, we've done the woodblock, the kick drum, and the snare. The last instrument in the arrangement is the hi-hats. Let's undo all of this. And go back to our trusty bandpass filter. While it would probably be nicer of me to spare you the tedium of scrolling back and forth through the effect list in Audacity, I feel it is fair to let you know exactly what you're in for when you use this software. With a little bit of experimentation beforehand, I figured out that 13,000 Hertz was pretty much good for our purposes. So, up we go. We can normalize this just to check to make sure. And then what you'll see here is that we've got very sharp sounds. We've got some crosstalk here from the snare, and we've also got the open hi-hat here. That might give us a little bit of interference and weirdness in terms of turning this into a driver, but it's something that we can cope with later on. As is, we now have the frequency ranges for all of the instruments that we want to work with and turn into drivers. So let's do that. So now back in Blender, we have an armature with a kick bone, a snare bone, a block bone, a hat bone, I'm reading the names here by the way, and a utility bone. The utility bone is where we'll be baking F-curves just like before. I'll add 4 custom properties in pose mode. This is edit mode, this is pose mode. Pose mode is blue and safe. This is yellow and stop, think about what you're doing. Anyway, edit all of these and we'll give each of these properties a name that corresponds to another bone in the armature. Snare and hat and block. There. Right. We'll hover over each of the properties once and press I so that we can get them up in the graph editor here, which means that we can now import just the tiny little slivers of the audio spectrum that we want for each instrument. So let's start with the block. Key, bake sound to F-curves. Lowest frequency, well, we were working with a median frequency and a bandwidth. So the bandwidth was always 20 Hertz, so I left it that way so it'd be easy to remember. So half of 20 Hertz is 10 Hertz. So to get your lower frequency, which we're doing right now, 2484, and the high frequency is half of 20, which is 10, plus the medium frequency, so 2504. There's the attack time and release time as well. Now you can think of these as smoothing functions effectively. The attack time is how long it takes for a sharp upward change of amplitude to register, and the release time is how long it takes for that same sharp upward amplitude to sort of peter off afterwards. Threshold and square threshold I'm not going to be worrying about. So let's bake that to F-curves, and we should see the woodblock. Ah, I've baked it at an offset. Not to worry. 1 key, bake sound to F-curves again, and we're back. Now you can see here the woodblock is head and shoulders above everything else on its channel. There is a little bit of noise, well not literally noise, but stuff we don't want further down in the channel, but we can take care of that later. Next is the kick. Key, bake sound to F-curves. The kick was, let's say, centered enough on 50, so we go 10 down to 40, 10 up to 60. and bake it. And I've done that thing again. Key, bake sound to F curves. Again, and now it's where it should be. Let's now go for the snare. Key, bake sound to F curves. Lowest frequency, let's see, it was 275 central, so 265 on the downside and 285 on the upside. Bake sound to F curves. I did it again. You can see the snare is head and shoulders above everything else on its channel. Isn't this fun? Key, bake sound to F curves. We're doing the hat by now. 13,000, 13,200. You might be asking why not do 12,900 and no 12,990 and 13,010. Once the frequencies get to a certain height or a certain amount, they're pretty much, one's as good as the other, so we can get away with this. I've done it again. Okay, I've done it again. It's getting late. What can I say? So there we have it. 4 different F curves. And that's looking pretty good. So now we can start to do other things. Let's set up some drivers. So we want to rotate on the x-axis, I believe. Yes, that's the head banging axis for our purposes. Very good. So, insert a single, no, not a single keyframe, insert a driver. Add a single driver. That's what we want to do. We just need to, because of the depth graph, we need to just jiggle that back and forth a little bit to make it come good. Right. So, drivers in. Now we get the data path for the kick. We go to the graph editor, switch to driver mode, X-Euler rotation for the kick, click, sneak, blick, no. Okay, single property, path, control V that in, value 1.4, var, and that should start headbanging for us now. Excellent. Now, let's copy that driver, paste, paste, paste. Then we go from bone to bone. Probably easy to do with the graph editor open like this. And get rid of that. Let's have a bit more room. Okay. Change the name of the path. Snake. Snake! That was a block, I believe. Yes. Block. And hat. Lovely. So. There's a bit of wrong with these. Each of these channels has a fair bit of noise in them. That is, stuff that we don't want. The hat should be okay, but it's a little bit underwhelming at the moment. We can probably get that head banging a lot better. So all we'll need to do is just multiply the var by about 8. And that should absolutely rock out. Lovely. Now for the kick. Going back to the F curves, we can see that the kick has a bit of noise down around here. So below this is stuff we don't care about. Above this is stuff we do care about. We can get the stuff that we do care about just by looking at the Y value. Now I'm going to round that off to 0.12. Again, we can use our old trick from earlier using max 0 var minus 0.12 and that's now still between beats. Again, we can probably make it party down a little bit harder. That is now one party dude. Bone. Snare. Oops. F curve. Snare. The noise level for this one's a little bit higher. So let's see, 1.34, 0.134, let's go for 0.14 as the noise threshold. And we can just steal the expression, Control C, Control V, 0.14, done like a dinner. I'd say we can probably amp up the rockitude of that. Okay, and now we just have the block to go. The block is also a little bit noisy, so let's reselect this, go back to the F curves, block. The block is very noisy. 0.194. 0.19, yep, 0.19 sounds good. Okay, drivers. Scroll down, copy the expression, paste the expression. 0.19. So that's looking pretty good. But I do see a problem. These two are the problem. And the problem is they just come down too quick and go back up way too quick as well. So we have the block and the snare to try and fix. So let's try and fix them. Go back to F curve, block, hit X to delete that, snare, and we can just put them back in. Doop, doop. Right, key. Let's see, let's do the block first. Back sound to F curves. Demo, now. 2494, oops, 2484 I should say. And 2504. Now, we make it go down faster by extending the release time. Of course, it helps to do the thing that I keep doing. Helps not to do the thing I keep doing, I should say. Okay, now our noise points are 0.224, I believe. So let's say 0.23. All right. Let's head over to the driver and set that as our noise value. 23. See how we go. Much nicer. Much smoother. Okay, let's do the snare next. The snare, go back to the F curve, snare, key, back sound to F curves, 265 on the low, 285 on the high. Let's try 4. And that did nothing. And you know why? Because I did that thing again. Back sound to F curves. Alrighty. Again, this is pretty noisy. Every time you increase the attack, the noise floor will jump up. So we're looking at about, just going off this thing here, around 0.17 on the driver, I'm guessing. Just eyeball on that. So from 0.14 to 0.17 and beautiful. We can take this accusatory box away now. Shoo. There we go, that's much better. So now we have a head-banging armatures. But didn't we say we were going to make a drummer? There he is. How did I do that? So you might be looking at some of these bones going, wait a second, Some of those are a kind of bluey, greeny, aqua, cyan, turquoise kind of color. Chartreuse? I don't know what color that is. Anyway, and you'd be right, because these bones, this one, this one, this one, that one actually, no, that one, thank you, right click, and this one, all have action constraints on them. So these are the sound bones, and this is the drummer. So an action constraint has a target and a bone. It can take a particular transform channel in local space, pose space, local with parent, etc., and then map that to an action on the armature that you're currently using. In fact, actions, as I found out while I was making this tutorial, apply to any possible thing. The bones just have to be named a particular way for the action to take effect. So we have here a target range, which comes from that fella there, and we have an action range, which comes from, if we go to the dope sheet, action editor, and there's a kick action that we can actually have a look at. We have to, okay, you see where the sort of thing got mangled there. Yes, that was the kick action, as a matter of fact. So that's the kick action. Just ignore everything else. Kick action. Smooth. So, turning that back on, I should say, and removing the kick action from the current thing. So, that's basically what the action constraint does. And we can set it up on that bone there, the snare. We can set it up on the block to do pretty much the same thing. We have an action for each particular little movement that we want him to do. So hypothetically, we could sort of make him jerk back and forth by adding an action constraint of some sort. So let's build an action for this guy. So let's start him off on, let's say, I don't know. Let's scale the chest in time. So we just pressed I there and set scaling as the thing that we are keyframing. And now we will scale him up a bit. Drop another keyframe. Change the action name to chest. Then add a bone constraint. Action. Target. Sound bones. Bone. Which one should we use? Let's use the snare. The snare hits you in the chest. Let's use the X rotation in local space to action. Chest. Something happened. Something tends to happen. You know, that's just how this thing goes. You know, something happens and then, I don't know. Anyway. 20 is apparently the thing that we want here. So 20. Then we want an action that goes from 1 to 21. So we have our chest action. We can now clear that. And sit back, press Control A. And that's how that works. Now obviously this is not a fully fledged character, this is just an armature. But the thing about armatures is that you can kind of make characters do what the armatures say. Now that is a very, very long topic for a very, very long tutorial. If you're interested in anything like that, go and hassle the guys at CG Cookie, because they can hook you up with a few tutorials about that. But that's about it for me. So, thank you very much for watching my inaugural Blender tutorial there. I hope you learned something you didn't already know. And if you have any damnation, praise, criticism, or jubilation to offer, please do so in the form of YouTube comments, possibly Blender Arts forum comments, and definitely hit me up on Twitter at Quollism, Quollism. Thanks again very much for watching, and I'll see you later. Bye.